do this on this computer this time. All right. Yeah, so I specifically bought it as a backup, but the wife has just been using it for fun. And so I have not used this or this pen. So how's this going to work? Okay, close enough. All right. I think we're in a functional stage, right? Good enough. All right, so today we're going to talk about integrability. Oh, it even writes differently. Right? Okay, so basically we've learned a bunch of things about integrability and or integrals and how to define them, and in a couple of very simple cases, how to actually compute them. Now, though, what we want is a bunch of theorems that we can use in order to figure out very quickly whether a function is integrable without having to go through that whole epsilon delta thing. Yes, I'm pretty sure I did put this in the 157 section, and then afterwards I'll go through and I'll see if I can fix it up, but it should be in there, yeah. In fact, if you pull it up now, you can probably see if it is in there. And if not, I'll just move it in after. All right, so we're just gonna like rattle off a couple of theorems almost immediately. So the first theorem will be the following. So if f is bounded, let's give it a domain. And monotone, then f is integrable. Okay, and I mentioned this pretty much when we were doing the f of x equals x as an example. I said, hey, look, this is monotone, and we did almost all of the work without ever actually having to use the fact that the function was x. And so that I was like, I drew a line. I don't remember exactly where it was, but I drew a line and I said, look, up until here, the only thing we've used is the fact that this function is monotone. And we're going to do something similar when we talk about integrability. And that's exactly what I'm saying is happening here, right? So it's almost exactly the same proof as f of x equals x, except now we have to keep the function a little bit more generic. So just, yeah, let's see if I can draw this. Now, I'm not even certain what colors will show up good on a white background, but let's find out. So probably yellow is not going to be good, but maybe green. What is this? Is this green? So if we say this is here is A and this here is B. Oh, no, I need a monotone function. Something like this, right? So what we're going to do is we're going to go through, we're going to cut it up into a bunch of equally sized things, at least as closely. Yeah, well, we'll see. Hopefully this works. I'm also so colorblind, I can't tell what colors are colors. And these aren't, I think, like obvious colors anyway. Like, what is this? What am I drawing in right now? Is that just red? Because it looks like it's pink in the thing at the top. Magenta? Oh, that's great. Okay, so anyway, the idea being, so if we draw our upper, and you know, you saw this picture, I think, when I drew it for f of x equals x, but if I draw like the upper and lower sums here, oh, that's a really kind of squished one. And again, hopefully what we see, exactly, yeah, monotone is increasing or decreasing. And in this case, we don't need strictly, so it could be non-decreasing or non-increasing. But again, kind of what we notice here. So again, when we subtract the upper and lower sums, we're going to get this like telescoping sum. So doing UFP minus LFP will give a telescoping sum. Right? And so the only things that survive, let me see if I can shade them in. Is a highlighter going to work here? Oh, I didn't draw the lower sum on this one, right? Sorry, let me draw the lower sum here. Okay, so the only thing will survive, oh, let's go like this crazy rainbow thing. So that one will survive. And then this one will survive, right? Because it doesn't have a friend to cancel it out. You remember when I was talking about friends canceling each other out, right? So these are the only two rectangles that don't have a friend that'll cancel them out. So these are, when we do the difference between the upper and lower sums, these are the only two that survive. And you can imagine if we really squish them down, right? If we make a lot of partitions, a lot of subintervals, we can basically make these areas as small as we want because their heights are capped. Their heights can only be so high. And then we're going to control the widths, and we can make the widths really, really small if we want to, right? So that's the idea. And now let me just double check which epsilon I want to use, because it's a weird one, right? All right, so for the actual proof, here's what we're going to do. So we're going to say proof, right? So we're really going to leverage the monotonicity in this case. And the great thing about the monotonicity is the supremum will always be the right endpoint of an interval, right? Because or in this case, let's assume we're increasing. So let's say without loss of generality. Suppose f is, well, let's say non-decreasing, right? Which again, some people say is increasing. That's the same thing. So let's suppose f is non-decreasing. And again, what we're going to have is that the infimum must occur at the left endpoint, and then the supremum must occur at the right endpoint, right? So we're going to take advantage of that. So let epsilon greater than 0 be given. And what we're going to do is we're going to choose a natural number really, really big, such that epsilon, such that, what do I want here? Yeah, 1 over n, is that what I want here? Let me just double check. I'm pretty, yeah, it should be, oh, no, I want f, yeah, it's a weird thing. So f of b minus f of a times b minus a all over n is less than epsilon. Okay, telescoping sum, exactly, yeah. So basically there's a bunch of like intermediate terms, but all those intermediate terms are going to die. So I say telescoping sum here, we'll see it explicitly come out, and when we do get the telescoping sum, I'll be like, hey, look, here it is, and notice that all the in-between terms cancel. So when you get that telescoping sum, only the very lowest term survives and only the very biggest one. Notice as well, because I assume that f is non-decreasing, everything on the left-hand side is positive, right? Or at least non-zero. I mean, I guess we don't actually know that f of b is not equal to f of a, because f could be the constant function. If f is a constant function, though, this is, it's done. We know the constant function is integrable. So we're going to assume that f is non-constant. F of b is strictly bigger than f of a. B is bigger than a. Left-hand side's all bigger than 0. Right? So that makes sense. Okay. So now choose the partition. So choose P. And again, the great thing is we actually get to choose what the partition is, right, when we do this. So I'm going to take it to be our good old friend, everything is evenly spaced. B minus a over n. Okay, so this is our partition of AB, and again, we can check, definitely things are increasing. The first, this should be xi. The first endpoint is A, right? And if we plug I equals n into this, you can do the math, everything cancels out and you get B. So this is a partition, and the great thing is the intervals of the partition here all have size 1 over n, right? Basically by construction. So we're going to choose P to be this nice uniform partition. So that, all right, so we're going to compute the upper sum, I equals 1 to n, of the soup. I'm trying to write here, bro. Okay, so again, I'm going to do this one maybe in a little bit more detail. And then when I get to the lower sum, B minus a over n. Yeah, absolutely, you're right. And again, so like I said, I'm going to do the upper sum in a little bit more detail, and then I'm just going to be like, oh yeah, the lower sum is basically the exact same, and we'll go faster. Yes, and she's a girl too, so I was giving her hell and I misgendered her. Okay, so because we're doing the soup and we're non-decreasing, the soup must occur at the right endpoint, right? So that's really where we're taking advantage of this. And then the length of the interval, b minus a over n like that. And let me just pull out the b minus a over n. Okay. Now, when you think about what the lower sum will be, it'll be the exact same thing. Instead of the soup, we'll have an inf. And then because we're non-decreasing, the infimum will be achieved at the left endpoint, right? So the left sum from I equals 1 to n. Or sorry, let me just go straight to the answer. We don't need to write everything all out again. So b minus a over n, sum from I equals 1 to n. And now we choose the left endpoint. And we could change the index if we want, but because I need to put these two together, I really want them to have the same index. So I'm just going to change, I'm going to use xi minus 1 to indicate that I'm using the left endpoint. And now when I subtract them, great, they both have this b minus a over n term. B minus a over n. And now here's where we're going to get our telescoping series, right? So I'm going to get f xi minus 1 minus, it should be, I was doing them backwards, right? Like that. This is our telescoping sum. Yeah, no, it's very similar, right? Just because, yeah, when you're doing x squared, you probably would have realized that almost because it is monotone increasing, right? I said only look at when a and b are greater than 0, just because it'll make your life a little bit easier. So it is very, very similar. And again, we get this like telescoping series here, right? Here it is. Right? And so the only thing that survives are the first and last terms. Well, oh, look at that. They just happen to be those things. And we guaranteed that that was less than epsilon, right? Sorry, I need a, why do we need, we don't have to. Yeah, exactly. Yeah. Yeah, so this choice of partition here at the top of the screen, that partition guarantees us that the sizes are equal, right? Like if you check, just compute what xi minus 1 is, right? There's a lot of like i's and minuses in there, but compute xi minus 1, which will be the length of the interval. And what you'll see is everything cancels. The only thing which survives is b minus a over n. So they're all the same size. Now you don't have to do that, but if you don't have to do that, then you lose out on a little, like you have to use like a less than sign instead. But basically what we lose the ability to do is pull out the b minus a over n term, right? The only reason we were able to do that is because they were constant. So I was able to pull them out of the sum. If you don't, you just say, choose some sort of partition whose widths are smaller than that. You totally can. And I think actually the proof in my book does that. So you can do that, but you have to replace it with like less than signs, right? So the I is given or can be, so it iterates, right? So the I here actually changes. So it's saying, oh, I should actually start at 0 here as well. So not at 1. Right? So it says plug I equals 0 into this. What do you get out? You get x0 is equal to a. Then plug I equals 1 into this, right? And so you get x1 is equal to a plus b minus a over n, and so on and so forth. So those are the points of the partition. And then when we sum, right, like I've summed over the same index, I've summed over I, just, to keep it consistent, I could have summed over something else, but that's the idea there. Right, and everything just nicely cancels. In the sense we have this kind of gross b minus a times f of b minus f of a thing, but whatever, that's not that big a deal. right? So boom, function is integrable, and we're done. Yeah, basically. And I mean, obviously we have to show that making n big enough works, right? And so this is, the actual showing that it works. But as a general rule, that should be true, right? If your function is integrable, then choosing a really, really big n should work. Just like when we were doing limits, you probably had a good idea that you could choose a really, really small delta, right? If you were given some epsilon over a billion probably would work, right? But of course you had to show that it worked. So same thing here, if we choose a really, really big n, make our partitions really have a lot of points, then yeah, we can probably guarantee that, the difference in the upper and lower sum is less than epsilon, but of course we have to actually run through it and do it, right? Okay, so, and as an immediate corollary of this, anything that is what do I want to say here? Anything which is a finite combination of bounded monotone functions is therefore integrable as well, right? In fact, maybe I should just kind of state this corollary. And you can use this. I brought this up in office hours yesterday. You can use this as well if you want, or rather you should prove this. Maybe let me call it a lemma or something. So if not to see. Okay, I'm going to let you prove this. When you're doing the additivity of domain question for the assignment, you might want to prove this instead. So if I give you, no, sorry, not from B to C, from or A to B, so from B to C. Then this function that's supposed to be a C, is integrable. What's the difference between a lemma and a corollary? I'll show you in a second. And it's like there really isn't a big one, like it doesn't make a big difference. Is integrable. Okay, so and hopefully you see if you prove this, you've proven the additivity of domain on the assignment, right? This is a little bit stronger because like I was saying in office hours the other day, you don't require that F and G have to line up at B, right? Whereas with additivity of domain, you are guaranteed that. So this is nice. So usually a lemma is something is a small result. It's not big enough to be called even a proposition on its own. And it's usually a result that's not interesting on its own. It's usually a result that you use to prove something more interesting, right? So it's a helper. You should think of it as like a helper result. Does that make sense? So lemmas usually immediately precede a bigger result, either a proposition, but not very often a theorem, just because they're often technical. Like if you have some sort of technical thing that you need to talk about and you don't want to put it in your proof, you can prove it to the side and call it a lemma. Now a corollary, so a corollary immediately follows usually a major theorem and is a consequence of the theorem. So it's usually a result that's not as big as the theorem itself, but is as a consequence. It's some sort of nice, interesting fact that the theorem proves, right? So it's like a chain of things. So you prove a lemma, you can use the lemma to prove a theorem, and then you use the theorem to prove a corollary, right? But the lemma is small, the theorem is big, the corollary is small. So the theorem is the main thing, the lemma is the thing that leads into the theorem, the corollaries are the things that come out of the theorem. But like, it's not a big deal. It's just naming things, right? These are all, in some sense, just mathematical results, and they're just the names that we assign to them. But we like to be able to signal as mathematicians the importance of a result by its name, right? Whether it's a proposition or a theorem or whatever the case might be. Yeah, it doesn't matter. Right, here, let me draw you something. So what I'm saying here, oh yeah, so I haven't proven the corollary yet, right? This is kind of a generic lemma. It's not related even to what we were doing just before. But here, so let's say, I've got, here are my axes, and then I've got, a function f like this. And then I've got some sort of function g. And again, like we don't really care what these functions are doing. And both of these functions are integrable. Then what we're saying is, on the whole interval, if we kind of like smush these two functions together, the whole thing is integrable, right? And what the area of the two halves separately is the same as the area of the whole thing, right? Like if we take the area of each part and add them together, we get the area of the whole thing. Yeah, exactly. So it's not monotone here. Now here's the corollary. So I'm going to leave this as an exercise. It's very easy to prove. Or rather, it's not easy to prove, but it's basically the same difficulty as question 1 of your current assignment. So if you can do that, you can do this. And the proofs are almost the same, right? They're almost exactly the same. And now the corollary. So if f is, screw it. No, let's be precise. If f from AB to R is a finite union, union is kind of a weird word for functions, but is a finite union of monotone functions, or we could say is a piecewise function of monotone functions. Maybe that one makes more sense. Is a piecewise monotone function. Then it's integrable. Okay, does that make sense? So what we're saying here is the previous theorem said if you're monotone, you're integrable. And now this corollary is saying, well, actually, you don't need to be monotone. You just need to be piecewise monotone, right? Because then what would you do? If you were piecewise monotone, you would take your function and you would break it into its monotone pieces, right? And really, this again should be like finite, right? You're only allowed to have finitely many piecewise monotone pieces. But if you break it down into each of its monotone components, each of those components is integrable. And then by the previous lemma, if you like smush them back together to get the original function, your whole function is integrable. Does that make sense? Right. So for example, now we could immediately say, well, yeah, x squared is integrable on any domain AB, right? It doesn't just need to be the positive things. It's true on any domain. So for example, so let's say let f be on the interval, let's say -1 to 1 to R, be the function which maps x to x squared, is monotone, or let's say maybe can be written. So in your assignment last week, right, we required that the domain AB, that A and B both had to be, I think, strictly positive, I think we said. And if not, A was greater than or equal to 0, but basically none of them could be less than 0, right? And that was just to make your lives a little bit easier. The point is now that even if I have something which is both, let's say the left endpoint is less than 0 and the right endpoint is bigger than 0, that's okay because it's just two monotone pieces basically, right? So this thing can be written as, f of x is equal to what I want. So let's just do, here, let's do this really dumb. right? And so this is very silly. And of course you wouldn't do this. But what I'm trying to illustrate here is on each of these intervals, in less than or equal to 1, on each of these intervals, these functions are in fact monotone, right? F isn't monotone globally, right? Because we know what the graph of F looks like, right? So here it's decreasing and then it's increasing. But what we're saying is, well, why don't we just cut that up down the middle? Look at its left part, which is monotone. Its right part is monotone. So that must mean that each of those parts is integrable separately. And then by the previous lemma that we had, if we smush them together to get back the original function, that thing is integrable as well. Does that make sense? And you can see you could do this with something that oscillates as well. You could take like sine, right? Because sine increases and then it decreases and then it increases and it decreases. And so each of those separate like monotone parts will be integrable. And then when you smush them together, as long as you only take finitely many of them, when you smush them together, you'll just get something which is integrable as well, right? So this is a really powerful theorem because it doesn't require a lot of conditions. All it requires is that your function is a finite piecewise monotone function, right? That it, so we can't do something like sine 1 over x because sine 1 over x near 0 like oscillates infinitely quickly. We can't do that. That one's a little bit trickier. So our function has to be bounded, right? So part of the definition of integrable is that the function is bounded. Tan x is unbounded, right? Wherever its denominator is 0. So in that case, yeah, tan x is not integrable. And we just would kind of throw it out. But yeah, any other function you can basically draw. Pretty much, I would say any function you could draw is going to work for this, right? Like most of you probably can't draw a function that oscillates infinitely often, other than maybe sine 1 over x. I'll give you another one later. But this covers so many theorems now, right? Or so many functions, right? Almost all the functions you can think of are now integrable using this theorem. Exactly, yeah. So for unbounded functions, we'll talk about improper integrals, but that's exactly the sort of thing that you need to use in those cases. So f negative 3 to 3, x maps to sine x. Can we cut out the monotone parts or something? Yes, absolutely. So you would take sine x, you would draw it, you'd cut it into its monotone pieces. You would say each part is monotone, and so you're integrable. As far as I'm concerned, though, all you need to say is, hey, look, listen, this thing is, finite. It's finite piecewise monotone, so it's integrable, right? We proved a theorem that said that's true, or this corollary, and so now you can just say that. You don't even need to do the math for it. You just say it. This is a great question. Exactly. So yeah, first of all, f does not need to be continuous. This, nothing about this theorem used continuity, right? There's no mention of continuity here. We're actually going to talk about continuity in a second, but nothing here requires continuity. And then there's this great question, can every function be divided into infinite monotone piecewise function? It depends on what you mean. As general, no. Right, yeah. So something like Tomei, so unless you're willing to say, that you can be monotone at a single point, which is kind of silly because monotone implicitly requires you to have multiple points which compare each other. But exactly, Tomei's function or the Dirichlet function, right, the characteristic function of the rationals, these functions, right, like kind of just constantly are switching. And so you can't kind of break them down into just a monotone collection of things. The more interesting question now, though, so Tomei is exactly a great counterexample. The more interesting question is, are there continuous functions that can't do that, right? So is there a continuous, basically what we're asking is there a continuous nowhere monotone function? I want you to think about that for a second. Is there a function which is continuous everywhere in its entire domain and is nowhere monotone, i.e. there is no interval on which the function is increasing or decreasing? Okay, so I'm actually going to show you one of those because the next theorem that we're going to do, oh, there absolutely is one. So this is, the part of the beauty of taking 157 is you begin to realize how terrible functions are, right? I think like your high school exposure to functions, all the functions you play with are really, really nice. Functions are terrible. They're like, real functions are absolutely nasty, absolutely nasty. Okay, so here, let me state the next theorem. Okay, so let's suppose I give you a continuous function. Yeah, exactly. Like everything is super nice, right? Is one of them a straight horizontal line? No. Yeah, so let's say, so for example, I would say a straight line, a constant function, is both non-decreasing and non-increasing. So in that case, it is monotone, and it's actually monotone in both directions. So I would count the constant function as being a monotone function. So if I give you a continuous function, continuous functions are integrable. Okay. And the reason why I very much specifically want to talk about the fact that there are continuous nowhere monotone functions is because if you give this to a student, a lot of what they want to do is the first thing they'll say, okay, well, every continuous function has got it. There's no way there's a continuous nowhere monotone function. So let's take our continuous function and let's break it into its monotone pieces. And then by our previous corollary, it's integrable. Bam, right? Super easy theorem. No, there are continuous nowhere monotone functions. So we need to prove it just for continuous functions separately. Again, most of the functions you can think of are going to both be finite piecewise monotone and continuous. And so both of these terms will apply. But yeah, I mean, there are continuous functions that can't be written as finite monotone things. So we can't do that, right? We have to kind of prove it from scratch. Okay, so let's see. For this one, the picture's a little bit harder to draw. I think, I can see it in my head. It's just I don't know if I'm going to be able to draw it. Basically, what we want to say is we know that a continuous function on a closed and bounded domain is actually uniformly continuous, right? Right? Yeah, we did that. This is one of those nasty, like in and around when we were doing, you guys don't remember that? Okay, so when we were doing close to intermediate and extreme value theorem, we proved this. Right? So you're gonna have to go back and look. Now, if I was on my surface, okay, great. Yeah. So if I were on my surface, I'd go back and look it up, but it would have been around, if you look up when we talked about uniform continuity, the theorem will be there, right? Whenever that was, October or something along those lines. So yeah, so it's uniformly continuous. Now remember, what does uniform continuity do? It guarantees that there's some sort of bound on how fast your function can grow, right? So it says, you give me an epsilon and there's a delta, which works everywhere, right? Such that f of x minus f of y is less than epsilon. Actually, maybe let me rewrite it because it's been a while since we did, and maybe you forgot what it means. And I say R here, but whatever the domain of the function is. Ooh, blue doesn't seem to be showing up super well. It's funny because it shows up well on my on the iPad, but maybe not as well in the screen share. But hopefully it's still readable. Okay, good. Yeah, good to know that it's still readable. It'd be nice if it was a little bit darker, but again, I'll maybe play with that in the break, or even better, find my pen. And remember, kind of the critical difference between this and continuity is this part right here, which says for every x and y, right? So it's not talking about, continuity talks about being continuous at a point C. This talks about, this is not true at a single point. This is true for every single point in the domain of your function, right? And it's some sort of guarantee on the bound of your growth. So it says, if x and y are within delta of each other, then there's no way that f of x and f of y can be further away than epsilon. So it bounds your growth. Now, where this is going to be really advantageous to us is if we guarantee basically that, what do I want to say? How can I say this? So if I choose my partitions to be really, really small, like let's say their length is less than delta, right? So if I choose my partitions to be really, really small, then I can guarantee that f of x, that the growth between f of x and f of y is never more than epsilon. And if you think about what the upper sum minus the lower sum is doing, that's basically a box which kind of covers your rectangle. It is a bound for how much your function can grow, right? So that's what we want to use. That's precisely what we want to use. In fact, do I have a function here? Here, let's do it on the x squared. Maybe let me zoom in here. So, right, let's say that this here is delta. And I choose, some x, and I choose some y here. It says that this distance here can't be more than epsilon, right? It's definitely less than epsilon. And the benefit of that, yeah, uniformly continuous implies continuity exactly. The difference is precisely that underlines thing that I drew. I'll zoom back into it in a second. But if you think about this, so now let's draw the upper and lower sum on this. Oh, it's getting a little crowded in here. But if we draw the upper and lower sum on this delta partition, what does it look like? It looks like this, right? This is the difference between the upper and lower sum, is that little box. And that, like, we're guaranteed that whatever, like, this box has a height less than epsilon, because no matter what 2 points I choose in this delta interval, their distance can never be more than epsilon away from each other. So the maximum height of this box is epsilon and its width is delta, right? So the area of this box is epsilon times delta. And that's what we're going to use, right? Because basically what I'm going to do is I'm just going to add up all these little boxes that we keep getting, whose heights are no more than epsilon, right? These heights are always going to be less than epsilon. And their widths are always going to be delta. And so when I add them all up, and I know exactly how many there are because I can control the partition, when I add them all up, I can guarantee that that number is very, very small. That's the idea. Okay, that's sort of the picture that we're going for here. Again, it's a little bit hard to draw. In terms of the difference, remember, so the definition of continuity here, I'm just going to write it out quickly. So continuity is you already have some point C in mind. Yeah, so here, you're continuous at every point. Right? And you're saying for every point, there is, exactly, yeah, exactly. Delta, yeah, your delta is going to depend on every point that you choose. So in fact, maybe I should put y here just so that it's kind of consistent with what we had above. So the difference is that up here, we have the for all y here, and for continuity, we just have the for all y there. And yeah, where does that make a difference? Exactly as Nicole says, here, because the delta comes after the for all, that means that this delta in the red or magenta or whatever it is, that delta is allowed to depend on y. But in the blue definition of uniform continuity above, because the y comes after the delta, right, that means that delta has to work for all y. So it's not like delta is not allowed to be a function of y anymore. It's not allowed to depend on y. It has to work for all of them. And that's why it's a uniform, right? It's there's one delta which works for everything, which is what uniform means in this case. Okay, so hopefully that helped. And okay, let's see if I can grind through this proof quickly, and then I will give you, maybe when we come back from the break, because that way I can set up a graph of it and everything. I'll give you this example of a function which is continuous but nowhere monotone. Okay, so let capital M be the max. And we know that these actually exist, right? Notice I'm not using sup and inf. I'm using max and min. And the reason for that is the function is continuous. And so by the extreme value theorem, we know these things exist, right? Did I say mean value? I meant extreme value theorem. By the extreme value theorem, right? Just double check here. Oh, you know what? Yeah, actually, this is not what I want to do here. Whatever, we can leave them. I don't think I'm actually going to use these. Okay, so let epsilon greater than 0 be given. And choose delta such that if x minus y is less than delta, then f of x minus f of y is less than epsilon over b minus a. Okay, so here we're using uniform continuity. Okay, now let's take a partition whose widths are at most delta. If we want to, we could do it ourselves, but I don't think it's necessary. So let's just say let P be a partition. Let's give it a name, x naught, x1, dot, 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 xn, be a partition such that, well, so that, whatever, such that the length of that partition is less than delta. And remember, the length of the partition is the width of its biggest subinterval, right? So what I'm saying is whatever partition you choose, we're making sure that the biggest subinterval still has length less than delta, right? So that's what we're saying when we write that down. Okay. So here's actually what I meant to write. So on each interval, xi minus 1 to xi, let mi be the min. I always hate writing this subscript here. This x in the interval. Okay, so on each interval, I'm going to let little m and big M be the min and max. And by the extreme value theorem, we know there's actually a point which achieves the min and max, so let's give them names. So in my book, I use these terrible letters. Maybe I should choose different letters because I'm writing on an iPad. So, oh, that's so bad. Okay, yeah, let's choose different letters. What are good ones? Mu and nu? Yeah, let's just use mu. So, and so let's say eta I. Yeah, no, let's use eta such that eta I and mu of I. No, because I use mu for measure. Okay, nu I such that f of eta I is m sub I and f of nu I is m sub I. Okay, so those are just the Greek letters eta and nu. If you're not familiar with them, they look like an N and a V, which is really annoying. So maybe they weren't great choices of letters, but whatever. You need exposure to your Greek alphabet at some point because we use it a lot in math. So exactly. Originally, right, I should have used Xi and Zeta because I'm not used to writing on the iPad, I'm just going to make a mess of them. But they are the worst Greek letters to write. So I should get you writing them earlier rather than later to get you used to them. Okay, so these are the points which actually achieve No, because I can't use x's because I've already used x's, right? So I could probably use like y and z. But again, if you get used to Greek letters, yeah, I could have used alpha and beta. But again, I want you to get used to some exotic Greek letters, right? There was a time when no one knew what the Greek letter Omicron is, and now everyone knows what the Greek letter Omicron is. But actually, that's a pretty boring letter because it's just, it looks like an O. Okay, so instead, eta and nu to be these. Okay, so clearly, now. Okay, does everyone agree with this? Yes, emojis. I don't know if I ever told you, we had a student 1 year who did his epsilon delta proof, but used houses and dragons. Have I told you this story? Yeah, so it would be like let house be greater than 0, and he would just draw a little house and choose dragon such that, dragon equal to the min of house over 4, comma, 1 or something like this. And so everywhere in his proof where he had an epsilon, he drew a house, and everywhere we had a delta, he had a dragon. Let me tell you though, like he got full marks because he knew what he was doing, but the marker was very pissed off because they had to like translate what was going on at every single point. And so I believe the comment was, "This is correct, but never again," sort of thing. So anyway, you could totally do that if you really, really want to, right? Okay, so is everyone okay with this? Yeah. So the fact that eta and nu have to be within the interval, right? Because we said little mi is the min, capital Mi is the max, but within that interval. And I'm choosing eta and nu, which achieve the max and min, but again, in that interval. So the distance between them also has to be less than the distance of that length. And we said that the maximal distance, like the maximal length of any subinterval of the partition is delta. So these two things are less than delta, which in turn, by uniform continuity, which is still at the very top of the screen here, implies that the difference between the max and the min is less than epsilon over b minus a. F of, which was, nu is the bigger one. I mean, you can put absolute values around all these things if you want, but I mean, everything is positive, right? Like so. Okay. And that's great. So that's what I was saying about, like, if you squish the intervals down, you can guarantee that it basically lives, the difference between the maximum and the minimum of the function lives inside of that epsilon box. Now, here we used epsilon divided by b minus a instead of just epsilon, but I wasn't going to write that for the picture. And so now your upper and lower sum, the great thing is that you have the max and the min. Well, the upper and lower sum, are exactly taken by the max and the min. So thus, right, if I take the upper sum and I subtract the lower sum, what is that? So I'm going to skip a little step here, but you can yell at me if this didn't make sense. Right? So basically, again, the capital Mi is the sup portion. The lowercase mi is the inf. I've just kind of smushed these together, right? The difference in the upper and lower sum will always be sup minus inf times delta xi. And now we've said, well, that is less than epsilon divided by b minus a. Right? But the sum, like, think about what that sum is. First of all, it's a telescoping series. If you actually write it out, it is a telescoping series. But alternatively, it's just the length of each of the subintervals, right? And you're just going to add up the lengths of all the subintervals. What do you get? Well, you get the length of the entire interval, which is b minus a. And that's what we wanted to show. Okay. Here, let me try and get that whole thing in the shot. All right, so there's the whole proof. Again, I actually didn't use this, so we can kind of like ignore this part. I didn't actually use this. Okay, and you can see, just like the monotone proof didn't use continuity, this proof doesn't use monotonicity at all, right? It's just a straight fact about continuity. Okay, so I think this is probably a good time. We'll take a little bit of a break here. When we come back, I'm going to write down for you, and I'm going to get the graph set up so that I can share my screen with you and you can see what it looks like. I'm going to share with you a function which is continuous and nowhere monotone to show you that we had to prove it this way. It wasn't enough to try and use the monotonicity result. No, I can't draw, and I'm certain that my dyno would be just terrible. Like, there's absolutely no way that this would be anything other than a complete and total embarrassment for me, right? Which, again, I usually don't have a problem with. I'm totally okay with being embarrassed like that. But like, what is it going to look like? Is it a T-Rex? I can't even I can't even draw legs. Like, wait, in a quadra, why am I trying? So we're bipedal, quadrupedal. So in a quadrupedal animal, their like back ankles go the wrong way, right? And probably they would have some thick thighs too, right? So we've got some like, I don't know. And then does that, so see, it's already bad. Like I'm not, I don't think it would, I will draw it for you a stick figure. Okay, we're gonna draw a stick figure T-Rex. This is my stick figure T-Rex. Is this part of his tail? Maybe we'll stretch his tail there. And then he's got his little short arms. And then can we Trogdor it? Like, okay, this is gonna be deliberately bad. So Trogdor, how does Trogdor's ears work? I don't remember. There we go. There's my stick figure T-Rex. He should probably have 2 legs, right? And 2 arms as well. There you go. Do you guys know, out of curiosity, do you know when I say Trogdor, do you know what I'm talking about? Yes. Okay. So literally only one person knows who Trogdor is. Okay, here, let me. So this is, listen, I don't want to say, okay, I had a student in Math 133 give me hell. He's like, do you know what memes are? I'm like, son, you merely adopted the memes. I was born into them, because there was a whole era of the internet that most of you, which is, again, I'm maybe an old man, but there's a whole era of like internet. Of course I know what memes are. Come on, give me some credit. Again, I was born into the memes. There's a whole era of internet like stuff and internet memes that you guys don't know existed because you just weren't alive at the time. So again, anyone over a certain age knows who Trogdor is, and everyone under a certain age does not know who Trogdor is. So I've put in the chat the link to the video. I'm pretty sure Homestar Runner is actually still up if anyone actually goes there. But this was one of the most like famous videos on the internet, I don't know, 20 years ago. So there you go, check it out. Let's take a 10-minute break. I'm gonna look for my pen and hopefully I can find it. And we'll see. So it's 10:12 by my watch. We'll come back at 10:22 and then we'll continue from there. Okay. And actually I might shut down the iPad because it's not currently plugged in. So I might unshare my screen and just throw it in and try and give it a little bit of juice. Okay. So I'll see you in 10 minutes. Not quite time yet. I didn't manage to find my pen. It was under my keyboard because I'm stupid. Right. So anyway, I do think there might have, like, the iPad wasn't recording in quite the same place. So I'm going to have to do some magic in order to make sure I can transplant those notes into the notebook. So you might have to give me a bit of time to make sure that that works out, because I'm going to switch back to my Surface. It was okay writing with the iPad. I didn't hate it. One thing though, I mean, you guys, none of you probably have experienced this, but like you probably, well, maybe you did. You might have noticed that my handwriting is different on the iPad than it is on the Surface. And that's just because, again, there's different, like, you know, the way that the pen flowed was different. Yeah, right, is different. And that's different than my handwriting in real life, right? So my handwriting on like paper is structurally very different. Let's see if I can find a good example. Yeah, here's something like wrong. I don't know if this is going to show up. So that's my like handwriting in real life, right? Which is different than my Surface handwriting, which is different than my Blackboard writing, right? Because when you write with on a Blackboard, there's a lot more arm and like heavy wrist, right? So it's very different when you write on a Blackboard. So my Blackboard handwriting is different, which is different than my whiteboard handwriting, because in a whiteboard, again, the way that you write, right, the way that you hold marker is different than the way that you hold a piece of chalk. And you try not to rest your arm against a Blackboard, but you can against a whiteboard, right? So yeah, it's true. I don't know what my sidewalk chalk handwriting is. It's actually probably close to my Blackboard writing. But basically, so for every different medium that you write in, you have a different handwriting style. And so I felt like a child again writing on the iPad, right? Because I don't have it practiced. Yeah, so that's kind of like a weird thing that you don't, I think most people don't experience until you start writing in different mediums. But if any of you get a chance, find a Blackboard when you're on campus and try writing on it, and you'll see your hand, it doesn't look anything at all like your handwriting, right? Like it's completely and totally different. So yeah, it's just kind of this weird thing where now there's like 5 or 6 different handwriting that I have. Oh yeah, okay, actually before I share my screen on the Surface, I'm gonna share it here because I didn't want to try and do this on the thing. Okay. So I saw some of you, I think, talking about the virus stress function, and absolutely the virus stress function is an example. So the virus stress function, technically, if you look up here, I've only summed from 0 to 10, right? Because, you know, don't ask Desmos to do too much, but at 10, you basically have captured the behavior of the thing anyway. If you plug in 100, Desmos can do it, but it kind of like really starts to slow down and lag. I was commenting the other day about how it's unfair to call this function pathological, and I'll explain why in a second. Right, okay, so, but here's the idea. So you can see, even just from, you know, I'm zooming in here, and you can see this function is very, very jagged. Now, because I only went to 10, we actually can zoom in enough that it will get smoothish, but even you can see, like, you know, out here, if we look at this section, it doesn't look too much like it's jagged, right? But as we start to zoom in, we see that there are, you know, these little jagged bits in here. Now, these parts actually are smooth, and that's just because, you know, I haven't summed all the way to infinity. I bet if I increased maybe this to 20 or something, yeah, so you can see like it starts to become more jagged, right? Like there's another little jagged here, and so on and so forth. Yeah, for sure, stock market-y sort of thing. And in fact, if you think about what's going on here, this makes sense. So think about here, let me zoom in again. You can kind of see this function in its wonderful totality. You can watch as Desmos tries to calculate this thing. So think about what the 3 to the n is doing, right? So as you let n get really, really big, the 3 to the n causes this to oscillate really, really quickly, right? So it goes, and it oscillates even faster. But then you divide it by 2 to the n, and the 2 to the n just, it keeps, basically ensures that when you add all these things together, it doesn't explode and go off to infinity, right? Because watch, if I kind of like get rid of the 2 to the n, maybe let me just replace by 1. Right, the function gets really, really big, and that's a problem because then we won't be able to sum to infinity, right, if they just keep adding on top of each other. So we don't want to add to infinity. So we have to make their amplitude smaller and smaller and smaller as we go. I'm going to change this back to 10 because it's a little too much. Right? Yeah, exactly. So what you're doing is you're adding more and more oscillations, but you're adding them in smaller and smaller magnitudes. And so that way this function doesn't like explode or do anything too crazy. But you know, you've got these parts that look smooth here, but eventually, right, as you add faster and faster oscillations, this will start to get jaggedy in here. And so this, okay, not on the entire, okay. What do you, sorry. Cat's on the keyboard. So yeah, that's the idea, is that it just starts to oscillate more and more quickly, but in smaller and smaller magnitudes. And so as a result, you end up getting something that is nowhere monotone. It basically is oscillating infinitely quickly at every single point. And so that's what goes wrong. For that same reason, you can probably imagine this is a function that ends up being everywhere continuous, nowhere differentiable, right? So this is another one of these kind of pathological examples for that reason. One of the reasons why, oh, cosine, oh, I believe it. Yeah, so you're oscillating super, super quickly. That one, though, you're not actually going to be able to sum to infinity. But yeah, I'm sure it starts to oscillate like crazy fast. But yeah, so that's the idea. As it was mentioned, right, this is often called a pathological function, but it's not at all fair to call it a pathological function. We think it's pathological because when we think of a continuous function, we think it probably should be, most of them should be differentiable, right? Or at least should be differentiable in a lot of places. But I think I've mentioned this in this class before. It turns out if you're trying to figure out, oh, how many, like if you take the collection of continuous functions, how many of them are differentiable just somewhere, right? And the answer is none of them, like pretty much none of them. There's a mathematical way to say that, it's called meager, but the collection of functions which are continuous and are somewhere differentiable are meager in the collection of all continuous functions, which means that this is what most continuous functions look like. Not necessarily exactly like this, but with these sort of like infinite oscillation things, that's actually how most continuous functions behave, because most continuous functions are nowhere differentiable. Just turns out that's true. Now, I don't know if most functions are nowhere monotone. I haven't done that proof. The proof is a little bit of work, but that is, is a thing, right? So keep in mind, these functions do exist. They are generally quite ugly. And yeah, you have to be careful about this. Okay. No, it's something called a Baire proof, B-A-I-R-E. So there's a very big, very beautiful theorem called the Baire category theorem. And it, like in old school notation, there's something called sets of the first category, sets of the second category, blah, 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 blah. I don't remember what it is, but like first category is meager, maybe second category is meager. Anyway, we don't use those words anymore in math. We use meager and stuff. And so it ends up being just a Baire category proof. It's a little bit more advanced than your typical, it's a relatively straightforward Baire category proof, but the first time you'll learn about Baire category theorem is probably in third year analysis. And the proof is slightly more advanced than a third year course. So by the time you get into fourth year, you could probably prove this. Unless you really went at it, right? Like if you were trying to specifically study the things you needed for this, but it's a fairly well-known proof. And it just uses the Baire category theorem. You don't need stuff much more complicated than that. Okay, so that's the idea. And yeah, I can tell you these things exist, but as a general rule, we don't have the tools to prove these things. I also can't prove for you that this function is continuous yet. We will do it in this class, but it won't be until like March that we have the tools to prove this is continuous. But yeah, this function is integrable, right? The moment you know this function is continuous, you get that it's integrable for free. You don't have to do anything because we just proved it, right? We proved that continuous functions are integrable. So that's cool. And the proof that this is nowhere monotone also requires a little bit of work, right? Like that's not at all obvious. I don't think we'll have the tools to be able to do that in this class, but I honestly don't remember what the nowhere monotone proof looks like. So, but even just proving that function is nowhere differentiable actually requires a little bit of work. Proving it's continuous is easy, but nowhere differentiable is actually quite hard. Okay, so like I said, it'll take me a little bit of time to reincorporate the two things. I would rather write with this though, because it is at least set up for me to write with. though we'll see if my stupid pen does stupid things, and then I'll get super angry and just say I should have gone back. But anyway, okay. So the last theorem that I want to do, or at least we'll probably have time to do, is the following. Okay, so if F maps A, B to R is bounded, and let's say D is the set of discontinuities. I think I mentioned this theorem to you before, of F, then if the measure of D is equal to 0, F is integrable. That's a slightly awkward way of saying this. I probably could have stated it a little bit better. But basically, if you take a function and it has measure 0 discontinuities, it's automatically integrable. So we know continuous things are integrable. Now we're saying, okay, well, what about discontinuous things? And the answer is, if its discontinuities have measure 0, you're guaranteed it's integrable. Okay, so that's what we want to do. We want to prove this. Is the measure 0 if and only if the points are not dense in any interval? Not if and only if. So for example, we have this example of a convergent sequence. So you can look at, for example, let's maybe just do this off to the side. So if you look at the set 1 over n, where n is a natural number, right? This thing has measure 0. No, and it is not dense in any interval. This is a good thing. Let me think. If you're dense in an interval, yes, I would say this is true, as long as we're careful about what measure 0 means, because as a converse to this, if you're dense in an interval, you might just not be measurable, right? So it's not even that your measure exists, it's that you might not be measurable. Does that make sense? So like, let's look at the converse direction, and we're saying, I give you a collection of points, or sorry, we're looking at the forward direction, but in contrapositive. So let's say I give you a collection, a set which is dense in some interval. It either has non-zero measure or it's not measurable, right? So we have to make sure that when we're saying the measure is 0, we're saying is measurable and the measure is 0. Does that make sense? It seems like a kind of a tricky little thing, but yeah, we have to be careful about that. Yeah. Yeah, so basically, if S is dense in an interval, it either has non-zero measure or it's not measurable. So it might be easier just to add that to the statement, the if and only if statement. That might be a little bit nicer to state. If the complement is dense in what? Like in R or in some interval of R? That might be the way of saying it. That's probably not a terrible way of saying it. If that's sort of a thing that, like, in practice, though, you wouldn't want to state a theorem like that because it's really nasty to check anything. But yeah, I think you have the right idea. It's just a matter of, like, how do we say this to make sure that we capture what we really want to say, right? It turns out, I don't know if I've said this to this class. I don't think I would have. So a set is Jordan measurable if and only if its boundary has 0 measure, right? And boundary being like the topological boundary that we discussed at the end of December, or sorry, beginning of December, end of November. That boundary, if your boundary has measure 0, then you're measurable, right? So yeah, or it's the Greek letter mu. Yeah. Okay. So the idea, and this is kind of a typical idea that one employs in analysis, is to put your bad points in a little epsilon prism. Okay, so we've got these points which are discontinuous, and we want to put them in a little epsilon prism. So we're going to do that. And the precise way that we do that is, well, we know that the measure is 0. So in particular, that means the outer measure is 0. So we can find a polyinterval which covers our discontinuous points. And okay, the polyinterval probably won't have length 0, but it'll have really small length, right? We could guarantee that it has very minimal contribution. Well, in this class, the only thing we're going to talk about is Jordan measure. So if you just say measure 0, it's fine, right? We won't talk about Lebesgue. So in part just because we don't know what a series is. Like we haven't, for some of you might know what an infinite series is. You've probably seen like an infinite geometric series, but the study of infinite series is a whole thing that we're going to do later in this class. We just haven't done it yet, right? So we can't talk about Lebesgue. Okay, so now here is, so let's say let capital M be the sup of F. And little m be the inf. Right? And epsilon greater than 0 be given. Okay, so what I want to do is, I don't think I'm going to choose my partition yet. Oh, no, I am. Okay, so since the outer measure of D is equal to 0, what about the rationals? Is it dense? No, yeah, exactly. The rationals are not measure 0. They're just not measurable. They're Lebesgue measurable. This is the important difference between Jordan and Lebesgue. Yeah. They're Lebesgue measure 0. They're just not Jordan measurable. Yeah. Okay, so since the outer measure is 0, right? And again, I'm using the fact that the outer measure, like we've assumed that the D is measurable and it has measure 0. So the outer measure is 0. And so this means we can find a polyrectangle or interval. We can find a polyinterval. What did I want to call it? I'm going to call it W. Such that D is contained in W, right? So W covers our set of discontinuities and 0 is less than or equal to, and will be actually strictly less than epsilon over 2m minus m. And again, this is one of these things where like, I know this is the right epsilon because I've done the work ahead of time. At this point, you would look at it and you'd be like, how did you get that? We'll see, right? We'll get to it in very quickly. Okay, so I've put it in a little prison. And now what I want to do is the following. So set, I'm going to set V to be A, B without W. Okay, let me maybe try and draw a picture of what's going on here. All right, so here's A, here's B. Okay, so we've got like 3 really bad points. Oh, maybe I should give you a point there. So here's our, this green thing. These are our discontinuities, right? And so I'm going to put them in a little prison like so, right? I'm going to just put like little intervals around them. And so the green stuff is W. Right? And V is all the yellow stuff that's left over. Right? So it's everything that's left over. And basically, what I'm going to do now, so there's a couple of ways of doing this. The way I do it in my textbook, I want to do it a little bit differently here. It's basically the same thing, but I feel like this one might be a little bit more rigorous so that people aren't getting upset at me. So what I'm going to do here is define for S a subset of AB, the function f of x, or sorry, f to the s of x, which is f of x if x is in S and 0 otherwise. Okay, so what I'm saying is I basically multiplied f by the characteristic function for S, if you want to think about it like that, if you know what those words mean. But basically I'm saying on the set S, f of x is just itself. Off the set S, it's just the zero function. Okay? Does that make sense? Does everyone see what this is? And the reason for that is that so that f is f of v plus f of w. Right? So v and w add up. V union w is the entire interval. So fv is going to be the portion of f, which is on the yellow bits. So in particular, it looks to be fairly continuous. And f of w is the other bits, right? It's the bits that contain the discontinuity of f. And basically what I'm going to say is, well, notice, so now f to the power of v is a finite piecewise continuous function, and so is integrable. Does that make sense? Here, maybe I can draw f of v. So f of v looks like this, and then it becomes 0, and then it continues to do what f does, and then becomes 0, and then it does what f does, and then becomes 0, and then it continues to do what f does, right? So that's the function fv. So it's continuous on each portion, right? That's the idea, is that this function is continuous on, each portion of v, and is a finite combination of these things because there are only finitely many intervals, right? We said w was I1. So in this picture, it would be I1, I2, and I3. And because what is f to the power of s? It's this thing right here, right? Yeah. And so we can guarantee that fv is integrable, right? By our previous lemma that says that if you just smush together finitely many integrable things, they're integrable. And the fact that we know that continuous functions are integrable, boom, we know that this thing is integrable, right? So there's a partition. Oops, not in green. Thus, there is a partition of AB such that UFVP minus LFVP is less than epsilon over 2. Okay, and I'm just going to refine this partition if necessary to guarantee that the endpoints of the intervals are contained in it. So if necessary, refine P so that the endpoints of the IJs are in P. Okay, so here I'm saying this red function that I've drawn above, which again is 0 on the green portions, but is just the function everywhere else. That function is integrable, so we can make the difference between the upper and lower sums arbitrarily small. Now, we have to deal with the green portions, right? So we've said here, f is fv plus fw, great. If I can prove that fw is integrable, then I'm done, right? Actually, maybe that actually is even a better way of doing this, because I know that the sum of integrable functions is integrable. So instead of trying to make this less than epsilon over 2, all I need to do is prove that fw is integrable. That actually might be a slicker proof. Whatever, we'll stick with what we've got here. Okay, so now I need to bound fw, right? So now, zoom in a little bit. So looking at FW, we have, so U FWP minus L FW of P. So what is that going to be? That's going to be the sum from I equals 1 to N of the sup minus the inf. And I hate this part, xi minus 1. I should just create some notation for the interval so I don't have to write this out a million times. Times delta xi, right? Now the sup minus the inf on any subinterval will be less than the sup minus the inf on the entire interval AB, right? That's the big M and little m that we wrote before. Times delta xi. Okay, but this is going to be 0 on everything except the I sub n's. Oh, did I use n twice? Hold on, let me just double check. Yeah, I used n here. So I should give, probably this will do less damage if I just change this to k. Okay, so let's say that there are k intervals in W. That's what I'm changing right here. Okay, because I used n twice. So this will be the sum from I equals 1 to k, m minus mi times the length of I sub I, right? And if I pull out the m minus m portion, oops, not m sub I, just m. This thing right here is precisely the size of that polyinterval. And that thing was less than, by construction, less than epsilon over m minus n. Actually, 2m minus n. And that's equal to epsilon over 2, right? So thus, UFP minus LFP is equal to UFVP minus LFVP plus UFWP minus LFWP is less than, here, let me put these in the brackets, epsilon over 2 plus epsilon over 2. And that's just epsilon, right? So we're done. And again, it occurs to me, this might actually, instead of trying to smush these together, again, just argue that f can be written as the sum of two integrable functions would do it, in which case you actually don't even need to worry about fv. You just need to prove that this function is integrable, and that's not too hard. So maybe that actually is an easier proof of that fact. It occurs to me. So if you want, try and rewrite it a little bit like that. That'd be a nice little exercise to do. And again, hopefully, why are these equal? Oh, at the very bottom? Yeah, exactly. Just the way that they are defined. So we know that generally, right, we can't split, like if I know that, what, h is equal to f plus g, we usually can't split those up like that without a less than or equal to sign. And if you want a less than or equal to sign here, that's totally okay. The great thing is that f is equal to fv plus fw, and one of those functions is always 0, right? When we say that f is actually equal to that, one of those functions is always 0, which means the supremum actually does do what you want it to do, right? Most of the time, the best you can do, let's maybe kind of do this as a side note, right? So normally, and this would be fine too if we did this, it actually doesn't affect the math. So normally the best we can do is this, right? And so that would mean that when I replace this by these things, I would have to normally put a less than or equal to sign here, which again, obviously doesn't actually affect anything. If this here becomes a less than or equal to, the math still holds. But in this case, it actually is an equal sign, because if you look at where this fails to be an equality, it precisely fails because f and g are both not 0, right? They both don't have to be 0. But in our case, we have f is equal to fv plus fw. One of these two functions is always the zero function, right? And that means that the soup here for this is actually an equality, not just an inequality, but actually an equality. So you can try messing around with this. I'm kind of leveraging on the fact that intuitively this is true, but if you want, you can go through and you can try and actually run the proof of this. But like I said, even if that's really bugging you, if you replace this equal sign here with a less than or equal to sign, it does not affect the math at all, right? Because you still get less than epsilon at the end of the day, right? But I think this is a good exercise and is worth kind of, right? You should have done this one as part of like the review stuff, but show that it's equality in this case. I think that's a good little exercise to do. Okay. As kind of another note, so if I'm going to go back up here to the theorem statement. So here, we have the statement that says if your measure, the Jordan measure of your discontinuities is 0, then you are integrable. If you replace Jordan with Lebesgue, it's an if and only if. Okay, so if your set of discontinuities has Lebesgue measure 0, then or you are integrable if and only if your Lebesgue measure 0. Your discontinuities have Lebesgue measure 0. Okay, so that's crazy. That's a super cool, super powerful theorem. We obviously don't have the tools to do it because we definitely need Lebesgue measure in order to do it. The other thing that makes it weird is that, again, you usually don't talk about Lebesgue integration in the context, or Lebesgue measure in the context of Riemann integration. Usually Jordan goes with Riemann, and then Lebesgue measure goes with the Lebesgue integral. But it turns out there's the statement on the Lebesgue measure relating to Riemann integration, which is a super cool sort of thing there. The Lebesgue integral, though, again, is strictly stronger. If you want to talk about whether a function is Lebesgue integrable or not, in that case, you can have full measure discontinuities, right? Your discontinuities can be gigantic, and you can still be Lebesgue integrable. So in that case, again, if we took like Thomae's function or the Dirichlet function, those functions are certainly not Jordan or not Riemann integrable, right? Like the Dirichlet function, the characteristic function of the rationals, was our quintessential example for a function that is not Riemann integrable. Nonetheless, the discontinuities of that function, or that function is Lebesgue integrable, but the discontinuities of that function is every single point, right? That function is nowhere continuous. So that function is discontinuous everywhere, but is still Lebesgue integrable. That's the power of Lebesgue integration, is that it allows you to measure functions or to integrate functions whose discontinuities are actually really, really big. Whereas Riemann integration can only integrate functions that have measure 0 discontinuities, right? So again, that's kind of a nice thing to take away from this. If you replace Jordan measure here with Lebesgue, it's an if and only if statement. And then if you want to think about Lebesgue integration at some point in the future, that's what it wins you. It gives you the ability to integrate functions whose measures are not, whose discontinuity measures are not 0, right? Okay, so are there any questions about that? Does that make sense? And I think this one's actually also very closely related to the assignment question. You can see in the assignment question, I tell you specifically that that the difference between F and G, right, that set is finite. And actually, it's enough that that set be measure 0, but at that time, we hadn't talked about, I guess I could have given you that problem. If you want to prove that problem for measure 0, you totally can. So again, you're in the assignment, I think the second question, you have two functions, and they disagree at exactly a finite number of points. But it turns out if they disagree at finitely many points, the result is, at measure 0 number of points, the result is still true. So if you want to do it in that case, you can. The proof is not that much more difficult. It's basically the same. But yeah, and it's strongly related to this. So this theorem here will give you a strong hint as to how to do that problem. Okay, any questions? Everyone's good? Additivity of the integral proof. I don't think I did, in part because I definitely forgot to think about it at all. So I will, yeah, okay, I'll try and remember to do it again. I'll write myself a little note here. Yeah, no problem. All right, everyone, hopefully that made sense. What we're going to do on Thursday is we're going to start talking about antiderivatives with the goal of starting the fundamental theorem of calculus next week, and that's how we actually compute integrals. So all this time we're talking about theory of integrals, how do we actually compute them? That's the next step. Okay, all right, cool. I'll see you all on Thursday. Yeah, have a good Wednesday, and I'll see you then. Bye, everyone.